Short person. Hi, everyone. So this talk is related to future sea level projections and a way to improve them using the collective state-of-the-art knowledge that we've been listening to for 3 days, but with a specific application, and that is to look at sites around the Antarctic coastline where there's infrastructure, for example, here McMurdo Station, or sensitive bioregions or other sites of interest. So these is in part a response to recommendations from the Decadal Antarctic Climate Assessment Report. And a couple of those recommendations are highlighted here. And that's, of course, to improve our understanding of the contribution of Antarctic ice sheets to sea level rise and communicate it to stakeholders what the impacts would be. And that's the aim of our project. And in fact, we submitted an information paper on this to the Antarctic Treaty Meeting this year, outlining what we intend to do, and we're promising a full study and a paper that will go with it. And the second recommendation that I pulled out here that we'll address is what do we need to do to improve these projections and particularly understand their impacts and uncertainties, and I'm going to show you that. Well, I don't really need to show that. We know the uncertainties in our sea level projections is what we're trying to improve. But when we talk about impacts on infrastructure, we're concerned about relative sea level around the coastlines. And so I took this from Jim Davis's website. And there's a couple of coastal effects that I'm going to run through quickly. You've heard about some of them. And of course, the gravitational effects that you see different signatures depending on where you are, what coastlines around the world you're at, and of course the influence of vertical land motion, which could be driven by tectonics, loading, or isostatic adjustment. So, I took this from an article in The Guardian entitled The Strange Science of Melting Ice Sheets, 3 Things You Didn't Know. And this is emphasizing gravity. This is their typo, not mine, I want to say. But what they're pointing out here is that if you lose ice mass, the ice mass is pulling gravitationally the sea level towards it, it rises. And if you lose mass, then that gravitational attraction decreases and sea level falls proximal to the ice sheet, and in the far field, that water is displaced to the far field and it rises. So this is what's behind sea level fingerprints, and on the right here is an example from Hay and others where they used 3D, a GIA model. And this represents if you uniformly melted across the West Antarctic ice sheet, the equivalent of adding 1 millimeter per year of sea level to the global ocean. And you'll see that the darker colors represent a normalized by global mean sea level rise. The fingerprint of the West Antarctic ice sheet melting is higher in the northern hemisphere, falls closer to Antarctica. But relevant to our purposes, I want you to look at this inset, which shows that proximal to West Antarctica, where the ice is being lost, there's relative sea level fall, versus in the East Antarctic coastline, you have a relative sea level rise. So there's considerable variation around the coastline of Antarctica that you would expect from the gravitational effect. The other one has been discussed quite a lot, rebound, the displacement of the Earth in response to ice mass loss and gain. And of course, this is more complicated in Antarctica. You've seen this discussed, and you'll hear more about this later in this session. But particularly in areas where we have marine ice sheet setting, the displacement of the bedrock surface has feedbacks that can potentially influence the evolution of the ice sheet going forward into the future. And in particular, to remind you, this is time 1 at a coastal margin of West Antarctica, and at time 2, although we have lost ice and the ice sheet has thinned, we have this sea level fall that reduces flux, and we have a rising bedrock that moderates the slope and potentially can elevate pinning points for the ice sheet, okay? So this is what we're concerned about, and thanks, Heiko, for talking about this effect, but these are some results from modeling done by Mariam Yousefi, who was a postdoc for our PolNet project and put together by Natalia Gomez and submitted for publication. And in a nutshell, a couple of key findings from this. This is a 3D coupled sea level ice sheet Earth model with 3D Earth structure from our seismic mapping. And what you find, and this is shown in the left panel, in a low emission scenario, there is that moderation of ice sheet retreat from the sea level feedback and bedrock uplift. And so there is lower contribution of the Antarctic ice sheet to future sea level in this scenario. But in high emission scenarios, which are shown on the right, the ice sheet retreats so quickly that the initial effects do not stop its retreat. However, because of the ongoing viscous response of the Earth related to rebound, this expulsion effect of these marine basins into the global ocean actually have the potential to increase the sea level contribution. Obviously, we are in the school that counts that as an ice sheet contribution to Antarctica. Okay, so to relate this to specific impacts, this is a conceptual diagram that Richard Levy made for our information paper to the treaty. And so we're looking at sites right at the coastline, proximal Antarctic islands versus far-field islands. And of course, here we're losing the ice. Here's our relative sea level fall. At the islands, we might have a small sea level rise because of this process of forebulge collapse that we just discussed, and in the far field, a sea level rise. So putting this in the context of infrastructure, of course, with sea level fall, we may need to change navigational access for ships to get to coastal station. We may need to move our infrastructure to lower elevation. But in the offshore island kind of scenario, you'd have to move it higher. And of course, it puts critical habitats under pressure. And in the far field, well, you may lose your terrestrial habitat. It's inundated and there's really no adaptation option. So what are we doing about this? What we want to know is for such different sites, how much, how fast, the question everybody's answering, and the way we measure sea level and understand the relative sea level component is normally through tide gauges co-located with a GPS station that's actually measuring the bedrock uplift so we can resolve relative sea level. This is what was used in the IPCC sea level projections, the tide gauge data, to understand the vertical motion. And so, unfortunately, there's a lot of low quality information. And so if we just look at the Antarctic coastline, red is poor, yellow is medium. And in fact, in the last IPCC, they only made sea level projections for 2 sites in the Antarctic Peninsula. So the question is, what do we do about this? How do we improve this? And so we need to improve our vertical land motion. Now, Tim Naish and Rich Levy and a larger group had just done an analysis of this kind for New Zealand. And so they were interested in pursuing this in the context of instant goals for Antarctica. And so they came to me and said, well, where are we going to get information about vertical land motion? And I was already part of an ongoing SCAR study from the Geodetic Infrastructure of Antarctica project. And we had started an intercomparison project, basically. So processing groups at Ohio State, where I am, Dresden, Tasmania, and Newcastle in the UK. are doing a project to determine a combined solution that will provide to the community to use for vertical land motion with uncertainties. That's our goal. And if you want to know more about that, Eric Bukta is leading the analysis, and he has a poster that you can go and look at. We thought, well, okay, let's use the results of this ongoing project for this problem. And so this just gives you a sampler. This is a different solution. This is from OSU for a subset of the continuously recording GNS stations, which I consider to give the most robust results. You can see these very rapid rise that we have in West Antarctica, and you can also see zones where the coastline is going down. The vertical land motion is negative. So what we're doing is then filtering that data to find sites that have robust histories that are in proximity to infrastructure, historical sites, specially protected areas, and critical bioregions of interest. And again, I'm just pointing out here that some areas are going down. If they're going down and sea level is rising, you've got a greater impact on whatever it is that you're concerned about. So our next steps in this project are to do sea level projections. Our plan is to do this using sea level ice sheet models coupled with GIA models to reduce the projections. And that's the next step in what we're doing. And importantly, one part of this analysis is to identify critical locations that do not have robust vertical land motion data. And so these symbols are specially protected areas, facilities, historical sites, and penguin rookeries. And so you can see there's a large area that has no information of the type that we need to improve our projections. So our goal is to incorporate this vertical land motion data to improve the projections. In order to do that, one requirement is that we need GNS infrastructure, either new instruments where we don't have sites proximal to sites of interest. We need longer time series, and where it's possible, these should be co-located with tide gauges. Thank you.
Great. Thanks very much, Terry. Because there's no talk after you, if anyone has a quick question before we let you go and have some coffee, feel free to ask. No, everyone wants a cuppa. So back here at what time, Tim? Sorry.